Alright, let's get into it. Today we're tackling a massive topic, one that's fundamental to everything we do in medicine: immunity. Think of it as your body's personal, highly sophisticated security force. It's working 24/7, tirelessly protecting you from an endless barrage of invaders, bacteria, viruses, fungi, and other nasty pathogens that want to set up shop and cause trouble. Without this system, a simple paper cut could be lethal, and the common cold could become a life-threatening illness. Understanding how this intricate network operates isn't just about passing your exams. It's about grasping the very essence of health and disease. It's the foundation for understanding everything from infections to allergies and even cancer. This system is your patient's best friend. It's what stands between them and a world teeming with microscopic threats. When it works well, we often don't even notice it. We go about our days breathing, eating, and interacting with the world, completely oblivious to the constant battles being waged within us. But when it falters, the consequences can be devastating. As future doctors and nurses, you'll be on the front lines helping to support and sometimes even manipulate this system to help your patients heal. That's why we need to break it down, piece by piece, so you can build a solid, practical understanding that will serve you throughout your entire career. So, what exactly is this, Guardian? Immunity is the body's capability to resist harmful microorganisms or toxins that can damage tissues and organs. It's not a single organ but a complex, interconnected network of cells, tissues, and proteins. We're talking about a system of checks and balances, of surveillance and rapid response. It can distinguish between self, your own healthy cells, and non-self, the invaders. This ability, known as self-tolerance, is crucial. A mistake here can lead to autoimmune diseases, where the body's own security force turns on itself. This is a concept we'll keep coming back to. Our journey today will take us deep into the two main branches of this defense system: innate and acquired immunity. We'll start with the basics, the general-purpose security guards that are always on patrol. Then we'll move to the specialists, the highly trained special forces that develop a memory and target specific enemies with incredible precision. This isn't just about memorizing facts, it's about understanding a dynamic living process. It's about building a mental model of how the body defends itself, so when you see a patient with an infection, you can visualize the microscopic war being fought inside them. Let's start building that foundation right now. To really get a handle on the immune system, you need to understand that it operates on two fundamental levels: innate immunity and acquired immunity. Think of them as two distinct but cooperative branches of your internal military. The innate system is your standing army, the first responders on the scene. It's the defense you were born with. It's nonspecific, meaning it doesn't care if the invader is a bacterium it's never seen before or a common virus. It treats all foreign threats with the same general set of tactics. Its response is immediate, kicking into gear within minutes or hours of an intrusion. It's your front line, holding the fort until reinforcements can arrive. On the other hand, we have acquired immunity, also known as adaptive immunity. This is your intelligence agency and special operations force rolled into one. It's not something you're born with, you acquire it over your lifetime as you encounter different pathogens. Unlike the innate system, this branch is incredibly specific. It identifies a particular enemy, learns its weaknesses, and then designs a custom-tailored attack to eliminate it. This process takes more time to get going, often several days, but the response is far more powerful and effective. It's the reason you usually only get chickenpox once. The key difference lies in memory. The innate immune system has no memory. It will react to a strep bacterium today the exact same way it will react to it 10 years from now. It's always starting from scratch. Acquired immunity is all about memory. Once it has fought off a specific pathogen, it creates memory cells. These cells are like veterans who remember the enemy. If that same pathogen ever tries to invade again, the acquired immune system launches a response so fast and so overwhelming that you might not even feel sick. This is the principle behind vaccination, which we'll cover in other lessons. These two systems are not isolated, they are in constant communication. The innate system does more than just hold the line. It acts as a crucial first alert, sending signals and presenting pieces of the enemy to the acquired immune system. This process, called antigen presentation, is what activates the specialized forces of the acquired response. So, while the innate system provides the initial broad-spectrum defense, it also sets the stage for the more targeted, powerful, and memorable assault from the acquired system. Understanding this partnership is key to understanding the full picture of our body's defense. let's dive deeper into that first pillar, innate immunity. The first part of this system is all about physical barriers, preventing invaders from getting inside in the first place. Your skin is the most obvious example. It's not just a passive covering, it's a formidable fortress wall. The outer layer, the epidermis, is made of tightly packed cells, rich in a tough protein called keratin. This makes the skin mechanically difficult to penetrate. Furthermore, the skin is slightly acidic, with a pH between 4 and 6, which inhibits the growth of many bacteria. It's also constantly shedding its outer layers, physically removing any microbes that have managed to cling on. It's a simple but incredibly effective strategy. Next, consider the passages leading into your body, like the gastrointestinal tract. When you eat or drink, you're introducing a host of foreign substances and microbes. The GI tract has multiple layers of defense. First, you have the powerful stomach acid, hydrochloric acid, which creates an environment with a pH of 1 to 3. This is lethal to most pathogens you might ingest. Further down, the intestines are lined with a thick layer of mucus that traps microbes. This mucus is constantly being moved along by the rhythmic contractions of the gut, a process called peristalsis, which helps to flush out potential troublemakers before they can establish a foothold and cause an infection. The respiratory system faces a similar challenge with every breath you take. The air is filled with dust, pollen, and airborne pathogens. To counter this, your airways, from your nose to your bronchi, are lined with a specialized surface. This surface is covered in mucus, creating what's called a mucociliary escalator. The mucus traps inhaled particles, and tiny hair-like structures called cilia beat in a coordinated upward wave. This motion constantly pushes the mucus, and everything trapped within it, up and out of the lungs, where it can be swallowed and destroyed in the stomach, or coughed or sneezed out. It's a brilliant self-cleaning mechanism. Finally, we have the urinogenital system. The urinary tract has its own clever defense. The constant flushing action of urine flow physically washes microbes out of the urethra, preventing them from traveling up to the bladder and kidneys where they could cause a serious infection. Like the skin and stomach, urine is also slightly acidic, which creates an inhospitable environment for many types of bacteria. In the female reproductive tract, the vaginal lining is protected by a community of beneficial bacteria, primarily lactobacillus species, which produce lactic acid. This maintains a low pH, suppressing the growth of harmful pathogens and protecting against infections. These physical and chemical barriers are our first and often most effective line of defense. When pathogens breach those physical barriers, the second layer of the innate system kicks in. This involves a cast of cellular and chemical defenders. Let's start with the cells, specifically the phagocytes. The word phagocyte literally means eating cell, and that's exactly what they do. They are the roving security guards and cleanup crew of your body. The main types you need to know are neutrophils, which are usually the first to arrive at a site of infection, and macrophages, which are larger, longer-living cells found in tissues throughout the body. When they encounter a pathogen, they engulf it, pull it inside, and destroy it using a cocktail of digestive enzymes and toxic chemicals. These phagocytic cells don't just wander around aimlessly. They are drawn to the site of an infection by chemical signals called chemokines, a process known as chemotaxis. Think of it like a 999 call for the immune system. Damaged tissues and other immune cells release these signals, creating a chemical trail that the phagocytes follow to find the trouble spot. This is a key part of the inflammatory response, the redness, heat, swelling, and pain you feel at the site of a cut or infection. It's a sign that your innate immune system has been activated, blood vessels are dilating to allow more immune cells to arrive, and a battle is underway. Alongside these cells, we have a powerful chemical weapon system called the complement system. This isn't one thing but a group of over 30 different proteins circulating in your blood in an inactive state. When they are activated by the presence of a pathogen, they trigger a rapid cascade effect, like a line of dominoes falling. One activated protein activates several others, which in turn activate even more, leading to a massive and rapid amplification of the response. This cascade can be triggered in a few different ways, but the end result is always to help eliminate the invader. It's a crucial support system for the rest of your immunity. The complement cascade has three main functions. First, it can directly kill bacteria by forming a structure called the membrane attack complex. This complex punches holes in the pathogen's cell membrane, causing it to burst and die. Second, some complement proteins act as opsonins. They coat the surface of a pathogen, essentially flagging it for destruction. This process, called opsonization, makes it much easier for phagocytes like macrophages to recognize and eat the invader. Finally, other complement proteins act as inflammatory mediators, enhancing the inflammatory response by attracting more phagocytes to the area. It's a versatile and powerful part of our innate defense. Now let's shift our focus to the second, more sophisticated pillar of defense: acquired immunity. If innate immunity is the blunt instrument, acquired immunity is the scalpel. Its defining characteristic is specificity. It doesn't just recognize a generic bacterium, it recognizes a specific strain of. This incredible precision is thanks to its ability to identify unique molecules on the surface of pathogens, known as antigens. An antigen is any substance that can trigger an adaptive immune response. The system then creates cells and proteins called antibodies that are custom-made to target that one specific antigen. The second hallmark of acquired immunity, as we touched on earlier, is immunological memory. After the first encounter with a specific pathogen, the primary response, the acquired system creates a battalion of long-lived memory cells. These cells remain in your body for years, sometimes for a lifetime, waiting for that same pathogen to show up again. If it does, they launch a secondary response that is much faster, stronger, and more effective than the primary one. This is why you are protected from many diseases after you've had them once, and it's the fundamental principle that makes vaccines so effective at preventing illness. This system also possesses a remarkable ability to distinguish between self and non-self. During its development, the cells of the acquired immune system are educated to recognize your own body's cells and proteins as friendly. They learn to tolerate them and not attack them. This process of self-tolerance is absolutely critical. A failure in this system, where the immune system loses its ability to recognize self, can lead to autoimmune diseases like rheumatoid arthritis, type 1 diabetes, or multiple sclerosis, where the body's own defense mechanisms mistakenly attack its own tissues. Finally, the acquired immune system is incredibly diverse. It has the potential to recognize and respond to literally billions of different antigens. This is possible because the cells responsible, the lymphocytes, undergo a unique process of gene rearrangement as they develop. This allows them to create a vast repertoire of receptors, each capable of binding to a different potential antigen. This ensures that no matter what new or mutated pathogen comes along, your body has a fighting chance of having a cell that can recognize it and initiate a targeted response. It's a system of immense power, precision, and adaptability. Acquired immunity isn't a single entity. It's divided into two major operational branches: cellular immunity and humoral immunity. Think of them as two different types of special forces, each with its own unique skills and targets. Cellular immunity, which is mediated by cells called T lymphocytes or T cells, is primarily designed to deal with pathogens that have already infiltrated our own body cells. This includes viruses, which must replicate inside our cells to survive, as well as some intracellular bacteria. It also plays a key role in recognizing and eliminating cancerous cells. Humoral immunity, on the other hand, is mediated by B lymphocytes, B cells, and the proteins they produce called antibodies. The term humoral comes from an old medical term, humor, which referred to the body fluids like blood and lymph. This branch excels at fighting pathogens that are found outside of our cells, circulating in these body fluids. This includes most bacteria, free-floating viruses that haven't yet infected a cell, and toxins released by microbes. The antibodies produced by B cells can't get inside infected cells, so they focus on neutralizing threats in the bloodstream and tissues. The core difference, then, is the location of the fight. Cellular immunity goes after our own infected or abnormal cells, while humoral immunity targets free-roaming invaders in the body's fluids. T cells are the assassins that directly hunt down and kill compromised host cells, or coordinate the overall attack. B cells are the weapons manufacturers, churning out antibodies that act like guided missiles. These antibodies can bind to pathogens, neutralizing them or marking them for destruction by other cells, like the phagocytes we discussed earlier. It's a perfectly complementary division of labor. It's crucial to remember that these two branches are not independent. They work in close collaboration. A key type of T cell, called a helper T cell, is essential for activating both branches of the acquired immune response. Helper T cells are like the field commanders. They assess the threat, and then give the orders to both the B cells and other T cells to ramp up their specific responses. Without the help of these commander cells, the response from both the humoral and cellular arms would be weak and ineffective. This interplay is a perfect example of the immune system's integrated and cooperative nature. So where do these specialist cells, the T and B lymphocytes, come from? Their story begins, like all blood cells, in the bone marrow. This is where hematopoietic stem cells, the master cells of blood production, reside. Through a process called hematopoiesis, these stem cells differentiate and give rise to various cell lineages, including the lymphoid progenitor cells. These are the cadets, the raw recruits that have the potential to become our elite B and T cells. It's here in the bone marrow that their paths begin to diverge, as they commit to becoming one type of lymphocyte or the other. For B lymphocytes, the bone marrow is both their birthplace and their training academy. They undergo their entire maturation process right there. During this time, they develop their unique B cell receptor, or BCR, which is essentially a surface-bound version of the antibody they will later secrete. This process involves that incredible genetic shuffling we mentioned, ensuring each B cell has a unique receptor. A crucial part of their training is a quality control check called negative selection. Any B cell whose receptor binds too strongly to the body's own self-antigens is eliminated. This is vital for preventing autoimmunity. Only the B cells that are both functional and self-tolerant are allowed to graduate and enter circulation. The journey for T lymphocytes is a bit different. While they are also born in the bone marrow from lymphoid progenitor cells, they are still immature and not yet functional. To complete their training, these pre-T cells must migrate to a specialized organ in the chest called the thymus. Think of the thymus as the elite military academy or boot camp for T cells. It is here that they undergo a rigorous maturation and selection process that turns them into fully fledged competent T cells. The thymus is most active in childhood and adolescence and gradually shrinks with age, which is one reason why the immune response can be less robust in older adults. Inside the thymus, T-cell cadets undergo both positive and negative selection. Positive selection ensures that the T-cells can recognize the body's own major histocompatibility complex, or MHC molecules, the molecular platforms used to display antigens. If a T-cell can't recognize MHC, it's useless and is eliminated. Following that, they undergo negative selection, similar to B cells. Any T-cell that reacts too strongly to self-antigens presented on those MHC molecules is destroyed. Only about 2% of the initial cadets survive this intense selection process. The graduates are mature, self-tolerant, and ready to patrol the body. Once they graduate from the thymus, mature T lymphocytes circulate throughout the body, patrolling the blood, lymph, and secondary lymphoid organs like the lymph nodes and spleen, waiting to be called into action. These cells are the master regulators and effectors of the cellular immune response. There are several types, but for now, let's focus on the two most important players: helper T cells, also known as CD4 positive T cells, and cytotoxic T cells, also called CD8 positive T cells. These two types have distinct but complementary roles in orchestrating the immune defense against intracellular threats. Helper T cells are the generals of the immune army. They don't typically kill pathogens directly. Instead, their job is to coordinate and help other immune cells. When a helper T cell is activated by an antigen-presenting cell, like a macrophage that has eaten a microbe, it becomes a command and control center. It begins to multiply rapidly and releases chemical messengers called cytokines. These cytokines are the orders that activate and direct other cells. They shout "wake up" to the B cells, telling them to start producing antibodies. They also cry "attack" to the cytotoxic T cells, authorizing them to seek and destroy infected cells. Cytotoxic T cells are the frontline soldiers of the cellular response, the assassins. Their primary mission is to find and eliminate any of your own body cells that have been compromised, such as cells infected with viruses or cells that have turned cancerous. They patrol the body, inspecting the surface of other cells. When a cytotoxic T cell recognizes a cell displaying a foreign antigen, like a piece of a virus on its surface, it locks on. It then delivers a lethal hit, releasing powerful chemicals like perforin, which punches holes in the target cell's membrane, and granzymes, which enter the cell and trigger apoptosis, a programmed cell death. This is a clean, controlled kill that prevents the virus from spreading. After an infection is cleared, most of the activated helper and cytotoxic T cells will die off. However, a small population of them will persist as memory T cells. These long-lived cells provide immunological memory for the cellular immune system. They remember the specific antigen they fought. If the same pathogen invades again years later, these memory T cells will mount a much faster and more powerful response, quickly activating the immune system to eliminate the threat before it can cause disease. These cells are stored in the lymph nodes, spleen, and circulating in the blood, ready for their next mission. Now let's turn to the other stars of the acquired immune system, the B lymphocytes. After maturing in the bone marrow, these cells also take up residence in secondary lymphoid organs like the spleen and lymph nodes, waiting for their specific antigen to appear. The main role of B cells is to produce antibodies, which are the key players in humoral immunity. When a B cell encounters an antigen that matches its unique B cell receptor, and it receives a confirmation signal from a helper T cell, it becomes activated. This activation triggers a dramatic transformation. Once activated, the B cell begins to divide rapidly and differentiate into two distinct cell types, plasma cells and memory B cells. The plasma cells are the antibody factories. They are much larger than resting B cells and are packed with the cellular machinery needed for mass protein production. A single plasma cell can secrete thousands of antibody molecules per second into the bloodstream and lymph. These antibodies then circulate throughout the body, hunting down their specific antigen on the surface of pathogens. They act like guided missiles, neutralizing toxins or tagging invaders for destruction by phagocytes and the complement system. Antibodies, also known as immunoglobulins or Ig, are Y-shaped proteins that have a few key functions. They can act as neutralizing agents, binding to viruses or bacterial toxins to prevent them from entering and damaging cells. They can also act as opsonins, coating pathogens to make them more tasty for phagocytes to eat, a process we also saw with the complement system. Furthermore, they can activate the complement cascade themselves, leading to the direct lysis of bacteria. Their structure allows them to be highly specific, with the tips of the Y forming the antigen binding site that perfectly matches their target. Just like with T cells, a subset of the activated B cells become long-lived memory B cells. These cells do not turn into plasma cells right away. Instead, they remain in the body for years, sometimes a lifetime, carrying the memory of the specific antigen. If you are re-exposed to the same pathogen, these memory B cells will quickly activate, bypassing much of the initial activation process. They rapidly differentiate into plasma cells, leading to a swift and massive surge in antibody production. This secondary response is what provides long-term immunity, and is the very reason we can live healthier, longer lives. Well, that's our deep dive into the incredible world of immunity. It's a complex but beautiful system, and having a solid grasp of these fundamentals will make everything else in your medical studies make so much more sense. If you found this helpful and want to keep building your knowledge base, make sure you follow us here at Joen Academy for more lessons to help you succeed on your journey. Keep up the great work.